calculus y and calculus how. Calculus, calculus y and calculus y and calculus how. So this is the discussion that we are proceeding. We started with kind of primitive calculus, the origin of the calculus, why calculus is required, and then from there we took it forward, and that is why calculus. From why calculus, how calculus, how why calculus is solving a problem, why calculus came into the picture, because without the requirement, without the need, no invention happens. Okay, so need is the mother of invention. So requirement is the mother of invention. So that is a kind of proverb, that kind of the necessity. The exact word is necessity is the mother of invention. So why calculus? That we talk, that if I need to have collection, if we are calculating collection, and then rate from the rate of collection, and rate of collection is constant, then multiplication works. If rate of collection is not constant and it is variable, then we go with kind of area computation. So if there is an area, if I have a rate of collection and I show it in a graph where independent component, dependent component, and there is a algebraic equation graph, and if we calculate the area, it becomes the net multiplication addition. So if if area gives me the net collection, let's proceed through the area. So only proceed through the area. Whatever graph you are drawing, sinusoidal, exponential, logarithmic, whatever, between this point to this point, what is the net collection? If you want to calculate from the rate of collection, then you have to just calculate the area. So from the area, there is a new fundamental came into the picture where algebra entered into calculating the collection. When algebra entered into the collection, then multiplication in terms of algebra, new name came as integral calculus or calculus. Calculus is integration, not differentiation. Differentiation came afterwards. So if we are calculating addition through calculation of area, where the area is nothing but width into height, and height is not constant, it is variable, then algebra comes into the picture. So variable height into width is nothing but a kind of algebraic multiplication. This is what we saw. So algebraic multiplication is nothing but integral calculus. So if I have a function fx, fx is height and width is x, fx into x is the area, where fx keep on changing based upon the x. Rather than saying fx x, people have started saying fx dx. Now it is calculus. And then lower limit to higher limit. If it becomes gx, then gx by x is fx. But since gx collection, the collection rate, gx by x is rate of collection, gx is net collection, collection by x, rate of collection is dependent upon where we are. At any point x, rate of collection, the rate of collection that I do, gx by x, is different. If that is the case, then gx by x, that was division, became the algebraic division. So now it became dgx by dx because it is calculus. So this is what we saw, and dgx by dx become fx, and fx dx becomes gx. Both are algebra. So anyway, we saw it nicely. Then if we, so gx by x, I mean dgx by dx to fx, so this is called derivative differentiation. Fx into dx integration, then it is integration, then it is derivation. If it is derivation, then integration is also called anti-derivative. If there is no limit we are setting, pure natural integration, then it is also called derivative. Anti-derivative. The derivative of sine is cos, then antiderivative of cos is sine. So now if we know the derivative calculation, that through first principle we can calculate the derivative. Through area calculation, what is first principle? Fx plus delta x minus fx divided by delta x. That is first principle. By calculation of area, we can calculate the integration. Now people saw that if I am not able to calculate integration of fx or area of fx getting gx, but if I see any gx function in the world for which the derivative is fx, then fx integration is gx. This way also people started proceeding. Now through area calculation we saw that x to the power n integration is x to the power n plus 1 divided by n plus 1. If that is true, then differentiation of x to the power n plus 1 by divided by n plus 1 is x to the power n. If that is true, then derivation of x to the power n is nothing but n x to the power n minus 1. One of thing is required, other is you can calculate. So if integration of sin x is minus cos x, then differentiation of cos x is minus sin x. So this is people started climbing the stair. How calculus? Why calculus? Because if you want net collection through rate of collection, then if you go through area way fx into x or fx dx, then it is integration. Why calculus? Because net uh, kind of coarse way of addition or multiplication do not work in rate of in calculating the collection where it becomes variable. When collection is variable, at each independent value the rate of collection is different. If that is the case, then integration comes into the picture. Why integration? How integration is? If I know the integration is nothing but calculating the area, then for each algebraic equation, what is the area? If it is x power 0, then area is x. If x to the power 1, then area is x square by 2. We saw triangle is half of the rectangle. If that is the case, then slowly people started climbing up. Let's calculate the integration of all possible algebraic equation or area. So if it is t to the power n, then it is t to the power n plus 1 divided by n plus 1. If that is the case, then what about sin x? If you are climbing from t to power 0 or x to the power 0, x to the power 1, then x to the power n is x to the power n plus 1 divided by n plus 1. Let's climb. What about sinusoidal? What about cos x? What about tan x? What about cot x? What about sec x? What about cosine x? If we do this, then what about exponential? What about logarithmic? What about this series? What about that series? What about Fibonacci series and this series and that series? So if that is the case, then let's proceed. So there are two ways. So one is that you really calculate integration from fx to gx, or if you get to have gx and through first principle means gx plus delta x minus gx divided by delta x, if you calculate so, then it becomes fx. So through first principle, through derivation also you can calculate the fx. If that is the case, then fx integration is gx. This way also people started proceeding. So like I don't like this way. First principle is the way where you have x plus delta x minus fx divided by delta x. This is okay, but approximation is something that you can prove it, but that is not concrete. Like if you say the derivation of sin x, that is nothing but sin x plus delta x minus sin x divided by delta x. So sin plus delta x is nothing but sin x cos delta x plus sin delta x cos x minus sin x divided by delta x. If delta x tends to 0, then sin x cos delta x. So cos delta x will become 1. This is what I don't like. So now sin x plus sin delta x cos x. So sin x plus sin cos delta x, where delta x tends to 0, then cos delta x becomes becomes 1. So sine x plus sine x, sine delta x cos x minus sine x. Sine x gone. So it becomes cos x sine delta x by delta x. Since both, if delta x tends to 0, both are tends to 0, even though they are not 0. So sine delta x by delta x tends to 0, means it is 1. This is what I don't like. But anyway, this is the first principle. So differentiation of sin x is cos x. Like if I take example of x to the power 2, if it is x to the power 2, then x plus delta x whole square minus x square divided by delta x. That will come as delta x whole square plus 2x delta x divided by delta x. That will come as 2x plus delta x. Now delta x tends to 0, I can take it out and it becomes 2x. But there are other way also, through first principle also. Like I can take x plus delta x, gx plus delta x minus gx minus delta x divided by 2 delta x at point x, left side, right side. Then the y side subtract and then divide by 2 delta x. If we do, then x plus delta x whole square minus x minus delta x whole square divided by 2 delta x. So it will result in 4x delta x divided by 2 delta x. It will result in 2x. This is completely clean cut. So if we proceed where we don't have to imagine anything, that is certainly better way. But anyway, we are proceeding that we found the sin x, ex, similar way you can watch previous video, and logarithmic everything. So finding the integration through area or finding the integration through antiderivative is also we have done. Through derivative or antiderivative we have seen. Now, there is one Mr. Taylor, he even proceeded when he saw that derivative can do much more magic. So, if I have any function x, I can create replica of fx gx where, where gx is only set of polynomial. Set of polynomial means gx equal to some constant or gx equal to x to the power 0 plus x to the power 1 coefficient I am not talking. So x to the power 0 plus x to the power 1 plus x to the power 2 x to the power 3 plus x to the power n. This is polynomial equation gx. Any function f can be represented as polynomial equation gx. This is what Mr. Taylor is saying, provided fx is ready to give the single 0th order derivative to nth order derivative to gx, then gx can replicate. At if it is at any point x minus a, then gx becomes f at a x equal to a plus dfx by dx x minus a plus d2 fx by dx square x minus a whole square by factorial of 2 plus d3 fx by dx cube at x equal to a into x minus a to the power 3 by factorial of 3 plus dn fxn by dx to the power n x minus a to the power n divided by factorial of n. There is one Mr. McLaurin. He is saying we can now, if that is the case, then let's try when a equal to 0. If that is the case, then we can replicate the many trigonometric equation also as polynomial equation. If a equal to 0, then gx equal to f at 0, dfx by dx at x equal to 0, x equal to a is 0 at x equal to 0. If you continue like this, then for sinusoidal, if we see, then f at 0, then sine 0 is 0. Then dfxy by dx, that will become cos x, x at 0 means it is 1. 1 into x plus d2 fx by dx square, that will come back in sine only, 0 means 0, gone, plus d3 fx by dx cube into x to the power 3, where a is 0, by factorial of 3. So sine triple derivation, first is cos x, and then again we differentiate, it becomes sin x. Again if we differentiate, it becomes minus sin x minus cos x. So minus 1 x to the power 3 by factorial of 3. So sin x is nothing but x minus x to the power 3 by factorial of 3 plus x to the power 5 by factorial of 5 minus x to the power 7 by factorial of 7. So this is Maclaurin. So Maclaurin said that if we are getting derivative, if this is fx black box, which is giving the derivative all order derivative to create the gx, then derivatives are at x equal to a, any point x equal to a. If a is 0, then we can represent any algebraic equation as polynomial equation. What is the importance that we have in a detailed manner we have seen? The bigger importance now, the bigger importance that we see is calculation of extreme estimation of extreme point. Like I have a sphere. Okay, I have really a sphere. So consider this is a sphere. Okay, and this is xy plane. If this is xy plane and a sphere is like this, so consider this is center. It is drawn as blue point. This is center. So this is sphere if we see, then it is kind of above the center. Now, if we see, then what is the extreme point? Extreme point maxima or minima. Then this sphere, the maxima is here. Can you see? The sphere is rising like this and it is coming to maxima and then going down. Down, 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 minima, then again it is coming up. So there is one maxima and one minima. Can we find maxima and minima? That is the case. So there are two things, maxima and minima. We saw in the sphere. Now what is the equation of a sphere? X square plus y square plus z square equal to radius square. Let's consider radius. Let's consider radius as okay. Let's keep it a only. So z equal to or fxy, the vertical fxy equal to square root of 1 minus x square minus y square. That is the equation of a sphere. Square root of 1 minus x square minus y square. If that is the case, then take xz plane. If this is x-axis, this is y-axis. If this is x-axis, this is y-axis. This is xz plane. This is yz plane. If I take xz plane, if this is a sphere, if this is a sphere, and if I take xz plane, then it becomes a circle. If I take yz plane, then it becomes a circle. For 3D model, we are talking about 3D model. If 3D model, if there is a surface, and surface I need to find maximum, the surface can take, it's like a mountain which has a peak and then which has a valley, peak valley, but it is in 3 dimensions. It is not a line. It is 3D surface that is taking a peak and valley. So peak and valley. So if that is the case, then if I see xz plane, then dz by dx should be 0 where there is extreme point. So dz by dx, so what is z? What is fxy? Square root of 1 minus x square minus y square. Let's calculate dz by dx. If I differentiate this, then it becomes 1 by 2 divided by square root of 1 minus x square minus y square into minus 2x. So 2 gone, it becomes minus x divided by a square root of whatever it. If I set dz by dx to 0 to get the extreme point in xz plane, it becomes x equal to 0. Okay. Similarly, dz by dy would be minus y by divided by something. So y equal to 0. At x equal to 0, y equal to 0, there is extreme points. True. So the sphere at center only above, there is a stream, but there are two extreme points. So whatever it is. Now, extreme point is maxima or minima that I have to calculate. If it is single variable, only x is the independent component, then double differentiation we can get it is maxima or minima. Okay, but here if I calculate double differentiation, then xz plane I can see it is maxima or minima, but not guaranteed it will behave same for the y-axis. If I calculate double differentiation d2z by dy square, then it will tell you the maxima in yz plane. Okay, so then again, like if we set dz by dx, then we get x equal to 0, x equal to 0, and dz by dy, if I get y equal to 0, they are not intersecting each other, so it's all right. Means x equal to 0 and y equal to 0, at 0 0 point a sphere has extreme points, but that extreme point is maximum or minimum. Through double differentiation we cannot calculate because there are two independent variables, one is x and one is y. If I do d2z by dx square, then I can calculate the maxima or minima in xz plane. If I calculate d2z by dy square, then I can calculate maxima or minima in yz plane. But there is no correlation, so not possible. Through double differentiation, we cannot say it is maxima or minima. If it is a single independent variable, then through double differentiation, we can calculate it is maxima or minima. Like, like if I have, we have done it. Like if I take a equation of a circle, then fx equal to square root of 1 minus x square. So that is nothing but minus x divided by square root of 1 minus x square. So that is the first order differentiation. Now the second order differentiation, if I calculate, then it will become minus x. So first let's differentiate with square root of 1 minus x square. So it will become minus x into minus 1 by 2 into 1 by 1 minus x square to power 3 by 2. If that is the case, then minus uh, okay, so I believe minus gone x by 2. Sorry, then after that again minus 2x. So minus 2x minus 1 by 2 gone, and then I had x already. I believe it will something come like x square. So I had earlier minus x, then minus x, and then again it came as minus 1 by 2 into minus 2x. So all gone, minus x square divided by 1 minus x to the power 2 by 3 plus plus or minus 1 by the square root of 1 minus square root of 1 minus x square. So this is the double differentiation I had never done. Now when x equal to 0, first term completely became 0. Next term is minus 1 by the square root of 1 minus x square. If that is the case, then when x equal to 0, it is minus in minus 1. Then this proves that the point at which we are calculating it is maxima or minima, then it is maximum. So this is the kind of we can get. If it is negative, double differentiation is negative at that point, then the extreme point is maxima. But here we cannot do. Unfortunately, how you can estimate? If you have, now if I calculated a d z by dx as minus x divided by square root of 1 minus x square minus y square. Now it has x and y both, means it is not possible. So how to calculate, how to estimate that our extreme point that we had got through dz by dx and dz by dy, setting it to 0, we calculated set of x and y points which are extreme point. These are maxima or minima. If that is the case, then let's see some ready-made solution. If I have parabolic equation, that is y equal to x square, fx equal to x square. Parabola has one maxima or one minima, global, that's it. Parabola, the way we showed, parabola is, has a parabola has a peculiar nature. Parabola has a peculiar nature that if it is like this, then it is global minima. After that, certainly there won't be any extreme point. If it is y equal to minus x square, then there is a global maxima, and down the line, certainly it is not going to turn back. This is parabola. So if fx equal to x square, then if it is a parabola, looking at the coefficient of parabola, immediately I can say it is maxima or minima. If fx equal to x square, the coefficient is positive, immediately I can say that it will have one extreme point and it will be positive, means it is minima. Fx equal to minus x square, then it will be maxima minus x square, then it will be minus x square, coefficient is minus, means it will have one extreme point and that will be maximum. So this is what we saw in parabola. Paraboloid. I really have paraboloid. This is paraboloid. This is a space typical paraboloid. Can we see this? If I cut in xz plane, then it is a parabola. If I cut in yz plane, again it is a parabola. So this is full case of paraboloid. Again, same nature of the paraboloid. So again, it is going on top and meeting it. Just don't see it. See half of it. See half of it. So this is paraboloid only till here. If that is the case, then it has one minima and then after that it is going to infinity. Now let's see top half. Then it has maxima, then down it is going to infinity. So if I have a paraboloid also, then looking at the coefficient, I can say it will make maxima or minima. Let's see fx equal to fxy. Earlier we had fx equal to x square. Now fxy equal to x square plus y square. If that is the case, then coefficient of x square and coefficient of y square, if both are positive, then it is this parabola, minima parabola, because they are positive. If it is minus and then in bracket x square plus y square or minus x square minus y square, if that is the paraboloid, then it will have one maxima and down it will go to the negative infinity. It will never we will have any extreme point. So if I have this kind of paraboloid kind of situation, immediately I can say that this is where it will have one maxima or one minima. This is what is possible, and that is maxima or minima looking at the sign of coefficient. Immediately I can tell it. Okay, so now I know I am not that weak. I am very powerful. If I know paraboloid equation, quickly I can say what it is. What about x square minus y square? If that is the case, then if that is the case, x square plus minus y square. If that is the case, then in xz plane it is like this, and in yz plane it is like this. Understood, right? In xz plane x square, positive coefficient, so it is like this. In yz plane minus y square, it is like this. It's like a horse saddle. The saddle you keep on the horse, it is like that. Means one side it is like this, and other side it is like whatever you can think about. So the point at which we are talking about x and y 0, at that point I cannot say it is maxima or minima, because in one plane it is minima, in another plane it is maxima. So if that is the case, but I have learned one. If I bring anything in x square and y square, I can say it is maxima, minima, or saddle point, or we don't know. We don't know. But it is extreme point. But that point is extreme point. That we have, if I say x square plus x square minus y square, then dz by dx, if fxy equal to x square plus y x square minus y square, then dz by dx equal to 2x, equating to 0, x equal to 0. And then dz by dy is minus 2y, equating it to 0, again 0. So at x comma y or 0 comma 0, it has extreme point. It is maxima or minima, that we don't know. But if we went ahead, then we saw it is a saddle point. It is neither maxima nor minima. But anyway, paraboloid equation or parabolic equation, immediately I can say then what the curve is. Now, are you getting the smell now? What I am trying to say? If I have any function fx, that function has extreme points at some point, at some x0, y0, x1, y1, x2, y2, x3, y3. I know there is extreme points, local maxima, local minima. How I calculated dfxy by dx, dfxy by dx, partial derivative, set it to 0. dfxy by dy, partial derivative, set it to 0. If you set it to 0, then you will get set of x and y points where there are extreme points. If these extreme points are maxima or minima, that we don't know. I cannot go with double derivative also. Then what would you be thinking? Oof. If somehow if fx was if fx was if fx was uh, paraboloid, then immediately I could have said it is maxima or minima. Hope so, fx equal to paraboloid. Not hope so, it's possible. That is Taylor series. fxy I can represent as a polynomial equation. That is Taylor series. Any fxy I can represent as a set of polynomials. Polynomial equation, Taylor approximation. So if I have fx, let's represent up to second order derivative. So now it is become gx. Gx is polynomial approximation of fx. Then gx equal to fab at point a comma b plus dfxy by dfxy by dx at x equal to a into x minus a into x minus a divided by factorial of 1 plus d2fx dfxy by dy into y minus b divided by factorial of 1 plus d2fx by dx square, d2fxy by dx square into x minus a factorial into x minus a whole square by factorial of 2 plus dfxy by dx into dfxy by dy at x equal to a and x equal to b. So dfxy by dfxy by dx into dfxy by dy. One is x equal to a and another is y equal to b into x minus a into y minus b divided by factorial of 1 plus 1 plus d2fxy by dy square where y equal to b, two independent components, right, x and b, y minus b whole square divided by factorial of 2 plus others I don't want. Only second order derivative I am calculating the approximation of fx as gx. If that is the case, then dfx by dx, dfx x, dfx by dx, dfx by dx, dfxy by dx and dfxy by dy are anyway 0. At extreme point, first order derivatives are anyway 0. If that is the case, let's don't take the constant f a comma b. Then we have dxy equal to d2fxy by dx square, x minus a, let's take x square. So d2fxy by dx square, x square by factorial of 2 plus f dfxy by dx into dfxy by dy, x into y, that's it, plus d2fx by y, d2fxy by dy square, y square by factorial of 2. Can you see this is like a parabola? The approximation of fx as gx at point a comma b, that is the extreme point. At a comma b, x is a and y is b. At that point, there is extreme point. At that point, I have to find this is maxima or minima. If that is the case, then fx I can represent as gx up to second order derivative. First order derivative, that is dfxy by dx and dfxy by dy, are anyway 0, because at extreme point first order derivative is 0. Then what is remaining is dfxy. Consider dfxy by dx as fx. We represent partial derivative as fx. So fx into x, fx square d2 fxy by dx, sorry, fxx into x square by 2 plus fx fy, fx xy, xy, x into y, fx into fy into x into y plus fyy into y square by factorial of 2. So this looks like x square is there, y square is there. So gx looks like an algebraic equation. Let's consider a full-fledged algebraic equation as ax square plus bxy plus cx square. Let's take any algebraic equation ax square plus bxy plus cy square. If that is the algebraic equation, I can transform it into a, and then big bracket, a and then big bracket. Inside that there are two brackets, a and then big bracket. Inside big bracket there are two brackets. The first bracket is x plus b by 2a, b by 2a whole square, plus in another bracket c by a minus b square by 4a square, and then bracket close, and then y square. So if I have any algebraic equation ax square plus bxy plus cy square, I can represent as a and then big bracket, inside that two brackets, plus one bracket plus two second bracket. The first bracket is x plus b by 2a whole square, plus in second bracket is c by a minus b square by 4a square, bracket close, and outside bracket y square. This can be represented this fashion. Now it comes to same as paraboloid, right? A is outside, all right. First bracket is x plus b by 2a whole square. So first whole square. The paraboloid equation is x square plus y square. So first square, that is x plus b by 2a whole square, plus next square is, next bracket is c by a minus b square by 4a square, bracket close, y square. So this is another square. This come as a paraboloid. If this is paraboloid come equation, then next bracket I can solve it. C by a minus b square minus 4 square will resolve in now 4ca minus b square divided by 4a square and y square. So now equation is x plus b by 2a whole square plus 4ca minus b square divided by 4a square y square. This is in bracket, then outside a is there. If that is the case, then it is a full-fledged paraboloid. Let's say go again ahead. Then now it becomes, the equation of paraboloid is x square plus y square. Now it becomes a into x plus b by 2a whole square, first one, plus second is a into, in braces, 4ac minus b square by 4a square, y square. So x square, y square. Now this is how it is. So first term will always be positive. That is a in braces x square plus b by 2a whole square. This term will always be positive, nothing to worry. Next is a and in braces, that is 4ac minus b square. That is the coefficient of y square. That is little dicey, whatever it is. Now we go ahead and we will again talk about what it is. So the actual algebraic equation is 4a square plus bxy plus cy square. I transform into a and there is a big bracket inside that 1 square and second square. 1 square is x plus b by 2a whole square plus second square is y square whose coefficient is 4ac minus b square divided by 4a square. Now consider the out that for the first x plus b by 2a whole square is always positive. Next is y square whose coefficient is 4ac minus b square divided 4a square. 4a square is always positive. 4ac minus b square. Consider that is positive. If that is the case, then a is kept outside. Now depending upon a, the paraboloid equation is decided. If a is positive, then it is minimal paraboloid. If a is negative, then it is maximal paraboloid, provided the coefficient of y square, that is 4ac minus b square, is positive. If that is negative, then it is a saddle point. If that is 0, then it is something that we need to calculate manually because second term goes away. If that is the case, then if I have equation like 4a square plus ax square plus bxy plus cy square that I placed as a paraboloid. Now I have here fxx x square by 2 plus fx fy x into y plus fyy square by 2. Then if I match this with the polynomial equation we talked about, ax square plus bxy plus cy square, then a is fxx by 2, b is fxfy, and c is fyy by 2. Now place this new ABC in the equation what we derived, and quickly you can check that it is the extreme points fxx, double derivative of fxy at point x equal to 1, a x at x equal to a, fxx is at x equal to a. So where a comma b is the extreme point, there can be many a comma b, x0 y0 x1 y1 x2 y2. For one term take a x0 y0. If x0 y0, then it becomes the a term. A term is dfxy by dx at x equal to x0 by factorial of 2. And then b is dfxy by a is d2fxy by dx square at x equal to x0 by factorial of 2. b ax square bxy, b is dfxy by dx at x equal to x0 dfxy by dy at y equal to y0, then nothing, no factorial is required. That is b. What about c? Cy square. C is d2fxy by dy square at y equal to y0 by factorial of 2. If I place there in the equation, then quickly I can say our fx at point x0 y0, it is maxima or minima. Then at x1 y1, because if I did first derivative, how we calculated extreme point? If I have function fxy, dfxy by dx set it to 0, dfxy by dy set it to 0, then you will get many, if it is kind of, it comes as a quadratic equation, you will get set of xy points where there is extreme point. If that is the case, then those set of points keep it, x0 y0 x1 y1 x2 y2 x3 y3, keep it. And then now place in the equation. Now we have a kind of Taylor series, second order Taylor series, that is fxx fxx at x equal to x0. The first one we are testing, fxx at x equal to x0 by factorial of 2. Another is fx fy, x equal to x0 y equal to y0. Another is fyy, that is dfxy by dy square fyy at y equal to y0 by factorial of 2. If you calculate, then internally you are calculating a b c, that is ax square plus bxy plus c square. then bring into equation, then now you have to check b 4ac minus b square is positive or not. If it is positive, then look for the sign of a. A is nothing but fxx divided by factorial up to at x equal to x0. That a is positive or not. If it is positive, then it is minima. If it is negative, then it is maxima. But if 4ac minus b square is negative, then it is a saddle point altogether. A is positive or negative. So only on the double derivatives you can quickly find out this way. This is the way that through double derivative you can find out it is maxima or minima. In single variable case, just double derivative, see the value, you can find out. But here double derivative, it is, you have to find along x-axis double derivative, along y-axis, and then x-axis, y-axis all together, and then you have to bring in equation like a and then x plus b by 2a whole square plus 4ac minus b square by 4a square y square. In that formula, if you bring and looking at some coefficient here and there, quickly you can say your fxy at points, set of extreme point, those are maxima or minima. So this is kind of usage of Taylor series in real life. Okay, we'll proceed on it. So you remember that we started discussion that how calculate. We go step by step and we calculate the kind of integration. So we started with polynomial x to the power n. What is the integration? Sinusoidal. Then we came to conclusion that sine delta x by delta x is 1. That's why sin x is cos x. We don't like this one. So we will calculate the integration of sin x. We had started the discussion, if you remember very well. The integration of sin x, that is cos x, without first principle. First principle is fx plus delta x minus fx divided by delta x by delta x tends to 0. Approximation. So purely through integration, means we know purely through kind of integral way. Integral way means polynomial integral, any way we know. So on top of polynomial integral, can we calculate sinusoidal? If I have sinusoidal and integral on and polynomial integral, can we calculate exponential then logarithmic? So step by step using the downward abstraction. This is machine learning. It is called deep learning. This is deep learning in machine learning or artificial intelligence. So that we will use and that we will see.